recording. All right. Hi, everyone, and welcome to the second day of our VSF Floquet Summer School. Just a quick recap from yesterday. I won't go through all the introduction. I will post some links for the website and the Virtual Science Forum if you would like to visit those pages. And I would like to thank again institutional support from Kavli Institute of Nanoscience Delft. Just a note that we are recording the talks, of course, and these will be made available as soon as possible on YouTube channel and on the school webpage. We now have the recordings from yesterday, and I will post the link to the YouTube playlist so you can access those. So the lectures are 50 minutes plus 10 for questions, roughly. And if you have a question during the lecture, please raise your hand and you can ask a question. If it's short, we ask that you defer longer questions or discussions to the end of the lecture. All right, so without further ado, I think Takashi is going to start the second part of his lecture. Thank you, Takashi, and you can get started.
Mm-hmm. Okay, so thank you very much, Babak. And let me share my screen. Okay, so everyone for joining to my second lecture for this Floquet Summer School. Before restarting the main part, let me go a little bit back to what I was I should have talked yesterday but didn't. So it's about experiments. So in the beginning of yesterday's talk, I mentioned several experiments related to Floquet physics. Okay, actually I forgot to add one more to this list, and there was a very nice experiment this year, so 2022. This is really fresh, and it's from Korea, and the people there, so they were working on Floquet physics, but it's really an interesting combination. So they measured or studied purely electronic realization of Floquet states in a superconducting device. So it's really a combination of graphene and a superconducting material where you basically have an Andreev bound state. So an Andreev bound state, but they can generate also this periodic driving using some electronic pulses. And so these are the spectrum. And so this direction, it's really like a strength of or intensity of this periodic driving. And they saw that the Andreev bound state, so the energy of the Andreev bound states show some replica formation. So in addition to the original band, you see these replica states. Schematically, they show it like this. So the original peak, in addition to the original peak, they have these side bands, and they interact with each other. So they hybridize with each other. So the amazing thing, or the very impressive thing about this is that there was no laser involved. So this was purely electronic. And also, so unlike those very strong laser-induced phenomena, which is usually done by pulse lasers, here this is a open Floquet steady state. So this Floquet state is realized and stays there forever. So I think, yeah, this is a very interesting experiment, and so maybe in the future people will start calling this kind of buzzword, Floquetronics. So using this kind of periodic driving in electronics. And yeah, maybe you know, but the combination of Floquet physics in superconductivity, there are many interesting theoretical proposals, such as Floquet topological superconductivity or Floquet Magnus states and so on. And probably, or maybe this kind of experiment will lead to such developments in the future. Okay, so this is something that I missed. I didn't talk yesterday. Also, one more thing. Go to the next slide. But let me also add a acknowledgement or a thank you to my collaborator. So if I have many collaborators in this project in Floquet theory, so I have to acknowledge many people, but if I were to pick one person, it would be Takuya Kitagawa. So this is from Google Scholar page, his Google Scholar page. He was an amazing super PhD student in Harvard. And okay, so you can see that his citations is really great, but he only did research for a few years, like 3 or 4 years. But he left a huge impact. Okay, and I collaborated with him in one paper like this one, where he discovered, he's the first one that really discovered that applying circuit polarized laser to graphene or honeycomb lattice, the effective model is the Hardane model. So that's what he discovered. That's this third paper. He also, I think, collaborated with Mars and other people. So so many important concepts and ideas in this Floquet community was actually invented by him. And after he left physics, so he has a very good career, not in academics, but in business. So he's really not doing very well in business. In a company, okay, in Rakuten, maybe probably you don't know this, but this is like Amazon in Japan. It's really one of the largest company, and he's really in a managing place there. Okay. So with that, let me resume where I left yesterday. So yesterday I was explain how to calculate the Floquet states. So in my talk, I basically start with a situation where I have a time-dependent Hamiltonian, and this Hamiltonian is time periodic. Actually, there are several other ways to realize a Floquet state, like a bang-bang construction where you have the time evolution operators originally, but in my talk, basically I will focus on the situation where I have a time-dependent Hamiltonian, and if I remind you, so these H0 and H+1 and so on, these are basically the Fourier transform of the Hamiltonian. And we are supposed to solve a big or infinite dimensional matrix problem where this big Hamiltonian is constructed from the original Hamiltonian, which has these Fourier modes. And you see that this structure, I have this omega and 2 omega and minus omega and minus 2 omega. So these, in the diagonal component, you have this additional m times omega shift in the energies. Okay. Also, I also explained this so-called Floquet space-time picture, or it's also called the Sambe picture. That this big Hamiltonian, you can view it as a Hamiltonian of a layered material. So if you start from like a one-dimensional material or a two-dimensional material, the resulting effect, the resulting big Floquet Hamiltonian, this infinite dimensional Hamiltonian, is something like a layered material. So if this was two-dimensional, this will now become a three-dimensional lattice with a static voltage or tilted potential in this artificial direction where this direction is really given by the Fourier index or Fourier mode M.
So Takashi, there is a question. Would you like to answer that?
Okay, yes.
Conan?
Hello, am I audible?
Yes, I can hear you.
Yeah, so my question was about this analogy of the space-time picture. So, as you said, we can kind of think of these Floquet modes as a kind of auxiliary system that has been, tensor producted to our original Hilbert space. So, I was just wondering, is there any physical meaning to asking questions like, can we perform a measurement on this auxiliary Hilbert space and collapse it to one of its dimensions and such things, or is that just a meaningless question?
Okay, so
just how far that analogy extends.
Yeah, this analogy is very nice. So you can also describe the Floquet topological states using this analogy in a higher dimensional material. So in that sense, this analogy is really nice, like a real analogy. But then if you really want to calculate some physical quantities, there are like a certain so yeah, it's okay. So this analogy in this higher dimension. So again, this index M is originally it's coming from this. Okay, so the physical intuition is a photon absorption. So the original band where M is 0 is your static system, and this when M is 1, so this layer, it's like one photon absorbed state, in which the energy is all shifted upward and so on. This picture, okay, so is also still valid when you couple this system to some external degrees of freedom. I will show you some picture related to this later. So maybe, please remember your question and maybe you'll find out.
Okay, thank you.
So, yeah. Okay, so then the next step. So then again, so there's okay. In the next slide, I'll try to explain how to construct effective Hamiltonian H of F. But pictorially, schematically, it's really the concept is to try to project out these states living in the other layers. So trying to integrate out the effect from the other layers and taking it to account as effective terms. Okay. So this is the next slide. So actually, I'm writing here one way to construct the effective Hamiltonian, and this is really like a most transparent and way to do this. So what I'm writing here is the time evolution operator itself, and I'm taking the logarithm of this. Okay, then you can see that. So I can expand my exponential, and you'll get like multiples. So like an infinite series of integrals of the Hamiltonians. You can also perform the integral that you obtain. And by doing this, you get a series expansion. This kind of series expansion is known as the Floquet Magnus expansion. And so I'm showing the first few terms in the Floquet Magnus expansions. So the first term is the static or the time average component of the Hamiltonian. And the second term is the 1 over omega expansion, or the 1 over m omega term. And it's the commutator of h of m and h of minus m. And you can see that it's really a series in 1 over omega. So here I have a omega square. And then there will be a omega cube and so on. You have multiple of these commutators. Okay. So actually, there are some mathematical difficulties from starting from here and obtaining this expression. Actually, this is not really a real true equal, but it's really like approximations. There are some subtlety in this expansion, which, okay, so one thing is coming from the fact that you cannot really uniquely define this, the logarithm of an exponential. So this is something like an exponential. And okay, so you can see that if I change my theta by maybe 2 pi or something like that, then I would get the same term. But if you do this, but that kind of ambiguity is are present in this expression. So this ambiguity, this ambiguity is there if this omega is not is like a moderate number. If omega is large enough and all your Hamiltonians are small enough, then this ambiguity becomes less and less. Also, another important thing is that, so in my talk, basically I'm just working on like a small size system. So this H is really just a small matrix, like a finite dimensional matrix. So okay, even in such situations, the convergence of the series is questionable. But basically for a finite size system, when omega is large enough, it does converge. But however, if you had a many body system or a strong like a interacting system, then this series, so you have this series of commutators of interacting Hamiltonian, and the size of the operators become larger and larger as you go further in the expansion, and this expansion is known to be divergent. Also, there is some subtlety that I didn't really mention, which is related to the initial time. So I said that I'm starting my time from 0 and doing it this interval up to capital T. But actually, in this expression, there was some initial time dependence. And if you really have done this expansion, there are some terms which is related to this initial time. But that initial time dependence has been dropped away. So yeah, this kind of ambiguity is there, but yeah, but again, you can still use this expansion to study the effective Hamiltonian in a finite size system. Okay. So then using this machinery that I explained, so this Floquet space-time picture, and also this effective Hamiltonian, let me try to study or reproduce what the experimentalists have studied. So this was the example that I mentioned already yesterday. So they're applying a circular porous laser to a two-dimensional Dirac system. So this sigma is a two-dimensional Pauli matrix or 2x2 Pauli matrix. And this A is a vector rotating within the XY plane. And they see this Floquet sideband, and so on. Let me try to calculate this Floquet bands within our formalism. So, so the model is like this. It's really simple. So
Takashi, there's another question.
Okay.
If you would like to take that. Srimai.
Yeah, so my question is related to this previous slide, the Floquet Magnus one. So you draw the initial time dependence, right? So in one of your paper, I actually saw the Van Vliet expansion also.
Yes.
And expansion is just gauge independent, right? So is it same as your Van Vliet one or different?
Yes. Yeah, thank you very much for mentioning. So yeah, so we have this paper with Mikami-san about the another expansions. Oh, I think this was the Brilliant expansion.
Yes.
There are like so again, obtaining this effective Hamiltonian. There are several ways to obtain it, and basically you get like a similar or equivalent results. One way to do it is more closely related to this picture. So trying to project out the states outside, and but still capturing its effect within this original Hilbert space. And to do this, you construct some kind of like a what do you call it? So this is the original Hilbert space, and I can introduce a projection to this states, and write down this kind of iterative iterations. And okay, so if you do this method, you if the result converges, they are basically the same with this Floquet Magnus expansion.
I see. Okay.
There are some ambiguities in this method, such as when you terminate your expansion, you get some artificial non-Hermitian terms in this expansion and so on, because you're projecting out other states. And maybe you can read this in more details in this paper in PRB in 2016. Yeah, thank you very much.
Thank you.
Okay. But then can I move into this part? So we're talking about this very simple 2x2 Schrödinger equation. So 2x2 Hamiltonian, and I'm having a Dirac cone and a circular polarized laser. So this A is now a vector within the XY plane, and it's really like cosine omega t and sine omega t, and this coefficient A is given by F over omega, where F, you can think that F is the electric field. So the electric field divided by omega, the photon energy. I also use this notation where my K is a complex number, but it's really just a momentum. So Kx plus I times Ky. So you can write the Dirac Hamiltonian in a very compact way like this with the circular polarized light. Then we can write this big Floquet Hamiltonian, so with the Fourier transform of this Hamiltonian. And if you truncate it up to this m to 0 and plus minus 1, it looks something like this. Okay, so let me again explain this step by step. So I have this big Hamiltonian. Actually, it's really an infinite dimensional Hamiltonian, so it will continue forever, but I'm now truncating it. The central block, the 2x2 block, corresponds to the 0 photon part. And yeah, if you diagonalize it, you obtain this Dirac band, which is like this X. And this red part, so this is the one photon absorbed state. So it's shifting up by omega. And this part, this block, my energy is minus omega. It's a one photon emitted state. So the energy is going down like this. And then, so this off diagonal terms. So if you include those effects and just simply diagonalize this Hamiltonian using some numerical code, you obtain a spectrum which looks something like this. And there are several features in this spectrum. So one is that, yes, so when the bands are touching, so let me move back. So here, there were points where the bands were touching. So the original band, this yellow, and the one photon absorbed state, they were touching here. And you can see that there's a gap opening. It's occurring as a, because this off diagonal term, so this A, those A's are opening a gap. And the size of this gap is proportional to A. So it's really like a one photon resonant gap opening. You can also find around energy 0, a small gap opening. If I, okay, like here. And this is their original, the experimental spectrum. And okay, so it's really not that clear, but you can kind of see those, yeah, this signatures or of this, the original band and this replica states. And also, okay, so I mentioned about this gap opening. So we were starting from a gapless Dirac cone, but now applying this circular pulse laser, you're opening a gap at this Dirac point. And actually you can analytically, yeah, it's so simple that you can analytically calculate this gap. And if you, it looks like this, and if you expand it in terms of A, it's given by A squared over omega in the leading term. Then, okay, so you see that this is starting from 1 over omega and so on. So we can, let's try to explain this using our Floquet effective Hamiltonian. Well, actually, this was what Takuya Kitagawa first discovered. So we were really simply starting from this very simple Hamiltonian. Again, it's the same thing. So this is Pauli matrix, and I have this sigma minus and sigma plus, a combination of just sigma x and sigma y with a I term. And this is, okay, so you can see that these are rotating. So it's moving in or oscillating in time. And if we use, okay, so I use H of effective, but this should, okay, so this is supposed to be H of F. H of F is, okay, so this is H naught plus 1 over omega times this commutator. And this commutator, H minus 1 and H plus 1, actually, you can just read it out from this Hamiltonian and as a coefficient of this oscillating term. So this H1 is given by, it's this guy, A times sigma plus, and H minus 1 is A times sigma minus. So its commutator, so the commutator of sigma minus and sigma plus will give you sigma z. So as a leading order in this 1 over omega expansion, you obtain A squared over omega times sigma z, which is precisely the gap opening term. So yeah, so this explains how to you open a gap around here. Okay, let me, okay, so this was to explain how you obtain this gap opening. Let me move on to lattice calculation. So just after, okay, so after our papers, there were several very interesting theoretical proposals of studying the transport properties in these Floquet states. Actually, in our paper, we also tried to do this calculation, but it was really a very naive calculation. In my paper, so what I was doing was to just study the situation where I have a voltage in this honeycomb lattice under circular polarized laser. But in my situation, I was studying the situation where I have a periodic boundary condition here and here. So it's really like a nanotube. It's really a nanotube, but having a circular polarized laser all over. And if I apply voltage, you get a current in this direction, a parallel current, but also a whole current. So that was nice. But my calculation, you can see these arrows. So these arrows are the static DC current. But this calculation was very naive. The system size was very, very small. But then there was a very impressive research work done by Babak and also Luis. And in this, especially what was very important was that they were studying this with an open boundary condition. So the point is that if we have an open boundary condition, having a circular polarized light, you get a chiral edge state at both of these side edges. Also, okay, so this was already in 2014, but they already went to a very extreme situation, or really like a cutting edge result even up to today, where they have studied a multi-terminal situations. I think experimentally, this is still like an ongoing direction in this field. Then, okay, so let me show you my next slide. So this is given by, actually I copied this paper from a review article by Mark. I think this is coming from Reese's paper, but the situation is like having a two terminal. So I have a electrode here and electrode here, and like a open boundary. So an open graphene sheet, which is very long in this direction, and studying the effect of this circular polarized light. And then what's really amazing is that, okay, so they have this very impressive Floquet spectrum, which has very many rich features. Okay, so first of all, this direction. So this is the momentum in this direction, and you can see, so these solid lines that that's highlighted. Actually, these are the edge state, but there are not just one like edge state, but there are like two types of edge states. The one is around the energy zero. Okay, so this direction, it's a Floquet quasi energy, which is the eigenvalue of this big. Okay, so you see a gap opening. So this was, if you don't have circular polarized light, it's a gapless Dirac system. So originally you don't have a gap here. But then applying circular polarized light, you open a gap here and here. But in a situation with the open edge, open boundary condition, you get this higher edge state. So in this part, like this lower boundary, you have an edge state pointing in one direction, like this. Okay, then of course the other interesting feature is that around here you get another set of edge states. So this blue lines. So you have two of them here and here. Actually, you can see 4. So here, here, and here, and here. But really, okay, so this now becomes a little bit subtle or difficult to absorb. But so in this Floquet picture, we have this Brilliant zone structure in the energy space. So meaning that, so you know that we're very used to the Brilliant zone structure in momentum space. So if you move one unit in the momentum space, so from 0 to 2 pi, then you'll see the replica or same state, same dispersion in the next Brilliant zone. Here in a Floquet system, you have the same structure in the energy direction. And basically, the size of this Floquet Brilliant zone is given by omega itself. Or here you have h bar of omega. So the first Brilliant zone is from here to up here. Then you're so basically it's supposed that you're in the same state again and again as you move in this direction, the energy space. Okay, but then in this picture, you don't see, it's a little bit different. You don't see such, let me first say that, okay, so from this Brilliant zone structure, this state that we have here is identical to the state up here. So although you see 4 blue lines here, actually this state and this state are the same state. So it's really like you're moving here, but actually you're restarting here. So you get this edge state, but then you see that the slope is opposite. So I have a slope going upward. Here it's downward. So you get an edge state which is pointing in the opposite direction at the Brilliant zone boundary. Okay, so that's one amazing thing. Then another thing. So I said that we have this Brilliant zone structure. So we're supposed to see the same structure repeating itself again and again if you move upward like this. So the copy of this should happen here and so on. But then you see that there are some difference, like the intensity of this guy and this guy are different. And somehow, yeah. So this picture here and this part is not the same. Actually, this is because what is plotted here is not the usual Brilliant zone picture, but it's the so-called unfolded Brilliant zone picture. So you can see this intensity of those Floquet states. Actually, you have as a state, there are the same state again and again as you move from here to this part and so on. The states are there, but as a color, so as a color coding, you can plot the static component of your Floquet states on top of your Floquet bands okay, so and by doing this, you get the picture in the unfolded Brilliant zone. But as basically,
Takashi, there is a question. Maybe.
Okay, yeah.
Yeah, Srimai.
This is.
Yeah. So my question is, during Mark's talk, he was saying that for C equals to 0, means star number equals to 0 sector also, there are some 8 states. And he said they are not protected by symmetry just due to time translation. Means if you have time translation, means this time translations means I am saying discrete time translation, they are protected. Now this pi 8 states you are talking about, this anomalous kind of 8 states, so they are protected by what? They are protected by any symmetry, or they are means they are just this time discrete time translation that gives them some protection.
This is not, so all the symmetry is broken in a quantum Hall state. So I think this is not protected by symmetry, but you have this winding number. Maybe Mark can correct me. But yeah, I think there's no symmetry which protect this edge state. So
this just become your like usual integer Hall effect kind of thing, time translation broken kind of stuff. So that is happening over here also. Means this gap is opening, due to that you are breaking some sort of symmetry here. Means
you're breaking the time reversal symmetry.
Time reversal symmetry, so it becomes your usual integer Hall kind of state. Okay.
Okay.
And I think Mark was agreeing in the chat. So.
Okay, thank you.
Yes, yes.
So one thing I want to mention here is that, I mentioned about this high frequency expansion, or one over omega. This is a really very popular concept in the Floquet community, but actually it's not like a ultimate theory or anything like that. It only accounts or explains the physics around energy 0, so around here. But you can see this kind of very peculiar and interesting phenomena, which is, I think, Mark. I don't know who invented this name, pi edge state. Maybe it's Mark. But so this state that appears at the Brillouin zone boundary, you cannot just simply capture it by using high frequency expansion, but yeah, it's there, and it's really like a very interesting signature of having a dynamical system. As a state, so it's the states around here, it's really like occurring due to a scattering of the original electron state and occupied state and an unoccupied state. So it's really like a resonance of electrons and hole, and it's really mixed through a one photon resonance. But this will also contribute to transport. Okay. So, okay, so now I'm presenting this. So if you have a problem like this that you want to study by yourself, then you have to find the ingredients or calculate this H0 and H+1 and so on in a model, but now it's a lattice model. Okay, so here, this slide, I'll try to explain how you can do this in a lattice system. Previously, I showed how to do it in a continuum model, which is the Dirac model. But for a lattice model, you can do something very similar, but there's a very nice way using the Bessel function expansion. So what we have is basically a Hamiltonian h of t, where the hopping term is hij. It looks something like this. So j of ij, this is the static part of my hopping, and I have this time-dependent phase factor where my a is the something like this. So it's really like an oscillating time periodic oscillating vector, and I have this like a distance or this displacement vector. So a vector from here to here, or in graphene, I have three possibilities. So I can move from here to here, here to here, so here to here. So I have three directions. So I have three combinations of this displacement vector. Then, okay, so the rest is really simple. So you can really explicitly write this term in, and it looks something like this. So it's a sine omega t with this additional term 2 pi of L over 3, where this L is this three directions. Then, then you, yeah, this, if you look into Wikipedia, there's a very nice section about Bessel functions, and you can find this kind of expansions. This J is the Bessel function. So the nth order Bessel function, for that I have this A, the coefficient here is A, and the phase that I had here will remain as a phase like this. Yeah, excuse me. So this, okay, so these terms are now my H of M that you have to put inside this big Floquet Hamiltonian to numerically diagonalize this. Already here you
I
can
think
see,
there is another question.
okay,
That's
yes.
Lavi.
Yeah. Hi, thank you. Takashi, in your previous slide where you were showing this graphene in presence of Floquet driving, I have a question from, yeah, just a bit before this one. Yeah. So the question I had is, it's a very naive question. So in the usual graphene without Floquet, you have like this Dirac cone at 0 energy. So I'm just wondering, like in presence of a Floquet, does it happen you have a Dirac cone also at pi? Because somehow in the Floquet I cannot decide which is lower energy. So there is like yeah, there is like, I don't know, I would have a hard time to define what is low energy, because I could always rotate the spectrum. So in that way I could think pi also as a low energy. So does it happen that I could have a Dirac dispersion as well as 0 and pi? So the edge states at 0 and pi both have the same dispersion, like they would move at the same velocity at the boundaries, or it doesn't happen?
So you're talking about this Dirac points at the K and K prime point?
No. So I tell them at energies. So at energy E equals to 0 and energy E equals to pi.
Here.
So, yeah.
So
do you have a Dirac points also at pi?
In the bulk, I think you do not have a Dirac point in this situation.
Okay, so what avoids, I mean, why doesn't this happen? I was just wondering because...
Oh, you just simply have a gap opening.
So is there a reason? Okay, I was just wondering because if I see Dirac, graphene in a low energy physics, I know it has a Dirac dispersion, but if I go along the lines of Floquet, then I could say that pi could also be low energy for me. I mean, I could, or maybe there is no way to define what is low. I agree.
What's actually, sorry. So you see this lower bands and the upper bands here. And basically what you're doing is I'm shifting this lower band up here by energy omega. So you see this faint
so that's why
structure here.
Yeah.
And then this original upper band and this lower band, which is shifted upward, they have this matrix element between each other, and that opens a gap here.
Okay, yeah,
This structure is very similar to what we had in the bulk Dirac cone. So it's really like I have this state and this part and have this term, and it opens a gap everywhere in the spectrum.
Okay,
so I mean, you don't have like a Dirac or Y point in this example, but you can actually you can find some examples like a three-dimensional Dirac system where you do have a like a pi Y point that occurs in the spectrum. So it really depends on the model you study. Here, the gap opens everywhere.
Okay. So I mean, in this case, then the dispersion for pi and 0 would be different. So they can have different velocity depending on, like, again, the model. I see.
Yes.
Okay, thank you.
Okay, thank you very much. Okay, so I'm coming back to here. So I'm now explaining these two terms. So I have a Bessel function and a phase term. The phase term here, actually this is, okay, so this may look very subtle, but actually this is a really very important piece in this Floquet engineering business. I think you can, Monica will talk about this in the context of cold atoms. So in cold atoms, people use this kind of phases as an artificial gauge field to introduce some magnetic flux in the system. So basically, if you have additional, so here it's just 2 pi L over 3, even if you have an additional phi, some phase, that phase will show up here as another phase. So if you have the ability to change your phase here, you can change the phase here, and that will lead to some magnetic field in your Floquet model. In the current situation, I will show you that this phase that we have here will lead to a flux in the Haldane model. Okay. And this additional, the Bessel function, this is related to the dynamic localization that I mentioned in the in yesterday. So you can, this is the, I showed how this zeroth order Bessel function looks. It starts from 1 and drops down. Maybe I will, so in cold atom, you can have a situation where this Bessel function really goes down to 0 and so on. In solid state, people also try to do this, but since, okay, so the laser in solid state is not that strong, but you can still go to a situation where this Bessel function will go down to somewhere around here, so maybe 0.9 or 0.8, already in 2014. I think now you can even go a little bit more. Okay. Okay, so now I have a small animation. So now I have an electron here, and using this hopping, let's imagine a situation where I'm absorbing. Okay, so let me move my blue dot here, here, and here. Okay, so I move my blue dot from here to a nearest and next nearest side. But during this situation, I was absorbing 1 photon and emitting 1 photon. So I was moving to a different replica band. So I was absorbing 1 photon and emitting 1 photon. At the end, I don't, so the photon is, the shift in the photon direction is 0. And through this process, I get an effective term, which is the Haldane hopping of K times I. Actually, in this situation, I obtain a phase which is pi. So I get I, this complex imaginary unit. You can also see this in a more professional way using this Floquet Magnus expansion. Okay, so in this nice paper, we have more terms up to 4th order if you want to do it. And also in this paper, it's really like a very long paper for us, but it's a very useful paper in the sense that we have an expression here in this paper that you can just plug and play. So you just calculate the Fourier expansion, this Bessel function expansion of this hopping, and then you can just plug it into a formula that you can find there, and using that you can calculate the effective terms that you obtain in the as a Floquet effective Floquet Hamiltonian. So in this situation, I get this Haldane hopping I of K, and it looks something like this. So I have second order a Bessel function square, and so on. You also have other terms. So long range hopping, if you go beyond in the 1 over omega expansions. Okay, maybe it's time. So okay, maybe no time to explain the Kubo formula, but it's okay. Oh, yeah. Okay, so in our nice paper in 2009, we formulated or modified the Floquet Kubo formula. The original Kubo formula is for linear response theory, but actually you can easily expand the Kubo formula to a Floquet state. If you look into the what's necessary to define a Kubo formula, it happens that if you understand the original state, okay, so the original state that we have here is a situation with a very strong laser field that is described by external a state described by Floquet states. If we have all the information of the Floquet steady state, you can do perturbation theory on top of it and study the situation where you have a very strong laser field, but if you have an additional weak electric field, you can generate a current. So you can generate a whole current, and yeah, this kind of actually it's a TKNN formula, but the ingredients here are extended to Floquet states and so on. Okay, maybe this is a good place to end. Okay, yeah, I'm going to stop here. So yeah, so using this kind of machinery, we can study this phenomena of having a circular polarized light in graphene, and you get the Berry curvature and the whole response generated by the laser. Okay, so thank you very much. That's all I wanted to explain in my 2 lectures, and I'm happy to accept questions.
All right, thank you so much. This nice couple of lectures. So there have already been some questions. We have time for maybe 1 or 2 more questions if you want to raise your hand, or I can also see if we have questions from the chat. Okay, Sumai.
Yeah, so my question is related to, you add one phase in, I think 2 slides before, where you discussed this e⁻² by, yeah. Before that, I think, before this slide, I guess before 2 slides before, I think, yeah, here. So this adding this phi phase and changing the initial time. So these 2 things are equivalent, right?
Yes, yes.
When you are saying that you are ignoring this initial time effect kind of thing and giving one Floquet Magnus expansion kind of formula, so then it will not take care of this phi effect. You are changing just you are just shifting the protocol by this. So how means then so physical observables independent of this phi shift, when it will be important? My question is, this phi shift will be important where?
So if you change the origin of the time, in this example, all 3, so we have 3 different directions, and all 3 of them will acquire the same phase shift, but the relative phase are the same. So you still have this phase, this one left behind, which will give you this like Haldane hopping. I think in quantum they can do even better in some sense, that they can introduce this phase and control it and make it different for each directions. Like you can have this direction and this direction and this direction, but have a different phase in each direction and so on.
Okay.
So I think this kind of
So
freedom
there
is there.
will be a like phase difference kind of thing, which is observable again. Okay. So, but if you change them like 5 phase shift for all hoppings, then I don't think that it's unique, because that will be same as changing that initial time. You have to do like, you have to change it separately for each hopping. Then it will be a phase shift and then it will be observable.
Yes. So you can have a phi dependent on L. And that will not be observed by like a gauge transformation. Or, shifting time.
Yeah. Okay. Thank you.
Thank you very much.
All right. Maybe a last question, Fabio.
Thank you, Babak, by the word. Takashi, nice explanations. Please, could you show again your slide with the experimental results by the time-resolved ARPS technique? Yeah, this one.
This one was okay?
The first. The
first one.
This
is okay.
Right. In some moment when you were explaining the matrix and the blocks to obtain its theory, right? You mentioned that is a possible theoretical explanation for these experimental results, right? Or this is in a really good agreement?
Okay, so I think this. I think they compared this. For example, they were focusing on the gap opening here, and compare it with this formula. And there they had a very okay. They claim that they have a very good agreement. And they also, I think, they had a theorist working with them, and I think they also compared the other part of the bands, and basically, so the state itself, so the position of the peak agrees. Then, so what's really not there in our theory, or this theory, is that the occupation. So this simple, like if you diagonalize this Hamiltonian, you obtain all the states, just the states like this. But then you also have to put the fermions or electrons inside the band, and there should be some occupations. In the experiment, they have this intensity, which corresponds to the occupation of the Floquet bands. And as for the occupation, that really depends on the scattering processes that takes place. So electron scattering and electron phonon scattering and so on, those information are somehow included inside the experiment. But actually, we don't really have at this point any theoretical, not any, but in this paper we don't have a theoretical understanding of that. But later on, many people try to study the occupation of the Floquet bands. That's really, actually, I think that's really even now important problem.
Right. Thank you, Takashi, for your explanation. Good.
All right. So thank you again, Takashi. And I think it's a good time to stop and move to the next lecture.